Okay, today we're going to be doing a linear approximation. So we're going to be dealing with functions that are a little bit windy, curvy, and all that, and we're going to find the equation of the tangent line like we've been doing. And then we're going to plug in a value close to that to estimate what that value is. Now, Mr. Record, when he did this, is he's having you find the approximate error in some of these. We're not going to worry about error. That is a BC topic. So we're only going to do the approximation of the actual Y value using a tangent line. So looking carefully at figure left, what do you see? While the figure may appear to be a circle, it actually has a 24 sides. You can see them, they're real small going around this thing. And when the number of sides becomes this large, the length of each side becomes smaller. So the calculus definition of a circle is simply a polygon whose number of sides approaches infinity. Now see, this would be approaching 24, and whose lengths of sides are approaching 0, because there's not going to be any sides. They're going to end up being a curve. So this is the definition of that. Okay, so the above phenomenon occurs quite a bit in the real world. Examine guardrails on the side of a curving road, and you will see that they do not match the curve of the road, but in reality are a series of straight line rails. Since the straight line sections of railing are numerous, they appear to curve. So in other words, each section, like from here to here, that would be a straight line right there, not really a curve. But they appear to curve because the more little sections you have, just like our circle, the more it appears to be curving. A wooden roller coaster is built the exact same way. Although they look like the turns are curved, they're really little slats of wood that are straight pieces of wood. Okay, that's why when you ride the roller coasters that are wooden, it shakes you up so much more than the ones that are made out of metal that actually are curved. So in linear approximations, like this curve right here is the actual f of x graph. This is the tangent line right here. This is the tangent line at this point. So we're going to try to estimate the y value using a line because it's easier to estimate that value than find the actual value. Although later on we will find the actual value. And this was usually on the AP test, and usually you're going to have to tell if your approximation is an overestimate or an underestimate. In other words, is the real function greater or less than your approximation, and we'll get to that later. So that's what we're doing on this. We're trying to approximate a different value other than A that's fairly close to A, and we're going to use the line to do it. So we're going to be finding tangent lines today. So using linear approximation means we want the tangent of the function of this at x equals 8. So we need the tangent line at x equals 8. So just like all the times, we need a point and we need a slope. And this says we're approximating. Now, do you see how this is cube root and it says cube root of 8? So we are actually approximating, and on your test, it will say approximate at x equal 8.1. So this is where we're doing our approximation at 8.1. So we're first going to find the tangent line at 8, and then we're going to approximate what it'd be at 8.1. So we need a point. So I'm going to do f of 8. When I do f of 8, that's going to be the cube root of 8, which is 2. So my point is 8 and 2. Now I want to find my slope. I need the derivative of f of x. So we need to think of this as being x to the 1/3 power. So this is going to be 1/3 x to the negative 2/3 power, which is going to be 1 over 3 times the cube root of x squared. So we're going to plug 8 in here to get our approximation. So I'm going to get 1 over 3 times the cube root of 8 squared. Now, I'm going to do the cube root first because I can do cube root or squared and then cube root it, but it's easier for me to do a cube root of 8. So this is going to be 1 over 3, and the cube root of 8 is 2, so that would be 2 squared, which gives you 4. Just like if you to take 8 and squared it, you get 64. The cube root of 64 is 4 as well. So this ends up being a slope of 1/12. So my my tangent line is y minus 2, because that's my y1, times 1/12 times x minus 8. So that's this line right here. And I'm approximating at 8.1 right here what the value of the graph's going to be using this. So I'm going to take this 8.1 and I'm going to plug it into here to approximate the y value. So we get y equals 112 times 8.1 minus 8, which I hope we can, and you can use a calculator on this if you wish. So this is going to be 112, and then that's going to be 0.1, which is 1/10, or 0.1 if you wish. So this is going to be y, this gives you y minus 2 is going to be 1 over 1/20th, and you add the 2 over. So that's going to give you y would equal 2 and 1/120th. That would be our approximation right there. So there's that problem. Now this says use a calculator, and we are not going to find the error. Okay, we are going to find the linear approximation of this, and we want to find it at e to the fourth root of e, which if you look right here, this is e to the x right there. So this means we're looking for it at x equals e to the x, and since this is going to, I should put this equals e to the 1/4, okay? So that means we are looking for it at x equals 1/4 because x is my exponent, and that exponent written is 1/4. So we're looking to approximate this when x is a fourth, and we are going to use this information to find our tangent line. So once again, we're going to do f of 0 to get our point is equal e to the 0, which equals 1. So my point is 0, 1. And then I'm going to do the derivative of this function, which the derivative of e to the x is e to the x. And then I have to still plug in my 0 to get my slope. So I'm doing f prime of 0 here, which equals e to the 0, which equals 1. So my tangent line is y minus 1, that's this one here, which is going to equal 1 times x minus 0. That is my tangent line right there. So now what I want to do is find the approximation when x is 1/4. So I'm going to plug 1/4 into here. So I'm going to get y minus 1 is going to equal 1 times 1/4 minus 0, which means y minus 1 is going to equal 1/4. So y is going to equal 1 and 1/4. This would be my approximation right here. Now this says to use a calculator. If you want to use a calculator, you can, but we're not going to worry about you using a calculator. If you want to put it in a calculator, hopefully you'll be able to do that. If you need me to show you, I'll show you later. And then we got one more, and again, we are not going to check for the error. We don't want the error at all. We want to approximate when x equals 4 plus h. Okay, and we're not going to find the range of h values. We're just going to make an approximation when x equals this, and we're going to do this at x equals 4. So we're going to use x equals 4 to find a point that goes with 4. So I'm going to do f of 4 is going to equal 4 squared minus 3 times 4 plus 5. So this is going to be 16 minus 12, 4 plus 5 is 9, so my point is 4, 9. Now I need to get my slope. I want to get my slope of this function. So I'm going to do my derivative again of this function right here, which is going to be 2x minus 3. So f prime of 4 is going to equal 2 times 4 minus 3, which is 5. So my tangent line is y minus 9 is going to equal 5 times x minus 4. And I'm estimating what this function is going to be at 4 plus h. So in other words, we're at 4 and we're just moving over h different. So that means I got to plug that number in right there and solve for y. So this is going to be y minus 9 equals 5 times 4 plus h minus, oops, I don't need a parenthesis there. So that goes in right there, and then minus 4. I hope you see these 4's cancel out. So we're going to get y minus 9 equals 5h. So y is going to approximate to be 5h plus 9. This is the approximate value right here, this thing right here. That's my approximate y value. So that's what you're going to be doing on this homework today, is doing approximations. Now, when on the key, he's going to actually have errors, but you should be able to find this approximation in the answer as well. So I will see you guys next time.